Howdy, howdy, and welcome to Physical versus Chemical Changes. The mini lesson fits perfectly with Science 9 matter and chemical changes. Let's get started. All right, so first things first, we're going to review what is a reaction. So reaction is where we kind of write it like this wonderful thing, like an equation. So we have reactants to start, and reactants make products. Once again, you start with reactants and you end with products. I'm going to shorthand this to like a capital R and then a capital P, just to make it a little bit easier. So we're going to look at chemical versus physical changes. So if you look here at chemical, notice here that my reactant is a log of wood. As it goes through the reaction of being burned, at the very end, the product, we end with a new substance or a pile of ash. When I compare that to my physical change or my physical reaction, quotation marks, pun intended, notice here I have my lemon to start, which is my reactant. I am cutting it with a knife. I still have my lemon at the end, so my reactant is equal to my product. Whereas my chemical reaction, my reactant does not equal my product. And I'm going to turn your head to the side, the equal sign, and the not equal sign. Let's go into greater detail about a physical change. So physical changes are generally reversible. I say generally because there's always exceptions to the rules. So a better sort of chemistry definition would be what you start with is what you end with. We shorthand this to my reactant equaling my products. So notice here that I start with water, a glass of water, H2O, and it's a liquid. I'm going to end with H2O and it's ice cubes, so it ends as a solid. I start with water, I end with water. The only thing different is it's going from a liquid to a solid. We call that a phase change. So a phase change is like a solid to a liquid, aka melting, liquid to a solid, or freezing, or sublimation, deposition, any of those phase changes we talked about in the previous lesson. Conductivity just means, does it allow electricity or heat to travel through it? Yeah, it can sort of like heat up a little bit, but once again, the wire is still the wire, or the piece of cotton is still a piece of cotton. Now, if the cotton lights on fire, that ain't physical anymore. Malleability and ductility are also physical. So just taking something like a solid chunk of something, and for malleability, we're pounding it into a nice, thin, flat sheet. Whereas like for ductility, you're taking it and you're putting it into a nice, long wire. I know I'm an excellent artist. You're welcome. Solubility means, does it dissolve? So for example, when I take my glass of water here and I'm going to add a powder into it, if it's soluble, it nicely spreads out and it looks like it's pure because it's soluble and it dissolves. If, for example, it is insoluble or doesn't dissolve, the powder would stay on the bottom. This is not a chemical because you start with a powder, right? And you end, the powder and a liquid, and you still end with a powder and a liquid. If I took either of these right here and I left them outside, the water would evaporate off. Or I could speed that up by adding heat to it. I can separate those. What is that called again? Yeah, a suspension. That's right, my friends. Or a solution if it fully dissolves. All right, hardness is our last one. This means like, can it be scratched? So if I take something and I scratch it, it is still the same substance. Nothing has changed. So we're going to flip over to our chemical changes or chemical reactions. These are generally not reversible. We call them irreversible. Once again, there are exceptions to the rules. So the better chemistry definition is what you start with is not what you end with. I like to shorthand this as our reactant does not equal our product. So when I look over here, you'll see that this wonderful molecule here, I'm going to give you a hint, is actually hydrogen peroxide, which is H2O2, is broken down into oxygen, and we see water here. It's broken down into two different things. Notice I start with these wonderful molecules, and it breaks out into two different molecules. Now, an example is a color change. So color change means it needs to be a distinct color change. So here I start with a yellow liquid and a clear liquid. When I mix them, notice I'm getting a red sort of substance in there, a red liquid or a red solid, a red something. That distinct color change tells you, bing, 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 it is a chemical reaction. We're going to compare this to dissolving. Notice I have clear water and red Kool-Aid. I end up with a red liquid. It is not a chemical change because this is red and it ends with red. Even if it's a lighter shade of red or a darker shade of red, it has to be distinct. Distinct. So now if I added red to like a clear liquid and it came out purple or green or yellow, that would be a color change. But this, my friends, is an example of a physical change. You're just dissolving something. or making delicious Kool-Aid. You're welcome. Our next one here is called an odor change. So this would be like when a skunk sprays you, or when like food goes moldy, or when you get like some kind of nice, beautiful perfumey smells. There's a distinct smell that you're like, oh, something is happening. Like when you're baking cookies. Cookies, delicious. All right, the next one here is producing a gas. You typically see those bubbles. So look at my example here, right? The clear liquid, we got a solid. This right here is the bubbles. It's bubbling and fizzing. That tells you a chemical reaction is taking place. This is not the same as when you open a can of pop and all the gas escapes, because the carbon dioxide gas was already inside the can. Notice this is open containers, right? It's a liquid. I dropped a solid in and I get bubbles. Our next one is producing a precipitate. Try that word with me, precipitate. This means making a solid. This has to be when you mix two liquids together. That's the only way. They go from clear liquids, they can be colored, to murky or cloudy liquid. So for example, we have this wonderful clear liquid here, clear liquid, and bam, a yellow solid is being produced. Sorry about that. Our next one here is, what is that? Clear liquid, clear liquid. Look at this wonderful fogginess. Ooh. I like to say it looks like ribbons as it's entering into the liquid. That's how you can tell that a precipitate is being produced. You'll also notice that over time, it will settle out because it's a suspension. Here's some more wonderful examples of what this looks like. When I say making a precipitate or solid, lots of times students think that as soon as you drop it in, it's like bam, it's like solid chunk of whatever would falls to the bottom. No, it's very murky, cloudy, kind of what it looks like. But as you leave it, because there is a solid there, it will settle out. Our next one we're going to talk about is actually a change in energy. So this can be like, for example, producing a sound like a pop sound or a bang sound, or the crackling sound you hear when something's burning. It could be like producing light. So light would be like a glow stick where you crack it and that's chemiluminescence and ooh, colorful. Or it could be like bioluminescence or things like that, but you're producing a light of some sort. And the last one here is temperature. We're going to look a little bit closer at temperature changes because there are two fabulous categories. The first one is endothermic. So endo, just like we broke down the words homo and hetero, endo is broken down into meaning enter or in. This means that heat is actually going into the substance. This is happening and it gets colder. So because the substance is colder, it's drawing in heat from the outside, just like this picture is showing. So heat is entering the substance itself. On the opposite end, we have exo. So exo just means to exit or exit. Oh, can I spell exit today? Exit. There we go. I can spell. So exo means that it exits it. So that means that energy is leaving the substance gets warmer. So we can see here on this side, the heat is going in, it's entering, it's endothermic because the substance is cooler. The substance is warmer, so it's actually releasing. You want to actually feel an endothermic reaction? My friend, stick some baking soda and vinegar in a plastic bag and hold it. It gets cold. It's crazy awesome. You want to feel something getting warmer? Well, if there's a candle lit, you can put your hands kind of around there. You can feel the heat given off by that. When something gets colder or warmer, bing, bing, ding, chemical change. So there's some examples here. I want you in your head to say, is it physical or is it chemical? All right, breaking glass. I'm hoping you're saying it's physical because even though it's in smaller pieces, it's still glass. Glass is glass is glass. Over here, mowing the lawn. I'm hoping you're still saying physical because short grass is the same as long grass, and that long grass is still there. Nothing has changed. Freezing a popsicle is still physical. You're just going from a liquid to a solid, which is a phase change. Spoiling milk. Yo, this is chemical. Why is it chemical? Because it stinks. And it also gets more like those solid chunkies in there. Oh, I'm feeling sick thinking about it. That is your evidence, right? And also color change sometimes too. But the biggest thing is that odor change is there. Odor change tells you it's a chemical reaction. How about slicing bread? It is literally just physical because one piece of bread or smaller pieces of bread, it is still just bread. Over here, we have roasting a marshmallow. Well, when you're roasting a marshmallow, it's chemical because A, the marshmallow changes color. It goes to a beautiful brown. It also smells like it. So you got a color change and an odor change. Now, if you light that bad boy on fire like my kids do, that is also chemical because now you can smell it. It got smoke. It's being exothermic, all that craziness there. Exploding fireworks, you can hear it, you can see a color change, and you can smell it. That means you are correct. It is a chemical reaction. How about squeezing orange for orange juice? Nothing changes. You start with the orange pulp and juice. You're just separating the pieces. Separating them does not mean chemical. When you go mixing Kool-Aid packs with water, I'm hoping you still said physical. That is just dissolving, right? And breaking an egg. Now, this one tricks people because they think, oh, I can't reverse it. It has to be chemical. No, my friends, it is physical. That's why I said it's generally reversible. Because, yeah, we can't put an egg really back together, but we start with an eggshell yolk and the egg white. We end with the eggshell yolk and the white. Now, if I cook that egg, if I cook the egg, I can smell it cooking. It changes color. That would make it a chemical reaction. But just breaking it is physical. Evaporating water is just a phase change. It is physical. So we're just going from a liquid to a gas. All right, burning wood, I can smell it. It's producing light, and my products are not equal to my reactants. Therefore, it is chemical. Popping popcorn, oh, you can smell that from a long ways away. It is delicious. It is chemical. Bleaching or coloring hair is a distinctive color change because you're coloring it. It is a chemical reaction. And finally, burning toast. Yeah, you know it's burning because you can smell it. Therefore, it is chemical. And the toast does change from light to dark. And melting chocolate, I'm hoping you saw it's a phase change. Melting chocolate is solid to solid to a liquid. Beautiful. All right, my friends, on a molecular level, what does this look like? Is it chemical or physical? So here we go. I'm going to look here. I got these two guys paired up. I got these guys paired up. This is my reactant. Over on my product side, I noticed that I have different things being arranged. This tells me it's chemical because my reactants do not equal my products. Down here, I start with this nice, beautiful, whatever this is here. Oh, look at that. My reactant and my product. These are two different things. So this tells me my reactants do not equal my products. Therefore, it is chemical. Over here, let's check this out, okay? Well, I got this guy and this guy. They're all beautifully arranged. Over here, oh, look, they're still here. This is literally going from a solid to a liquid. So this tells me that my reactants are equal to my products, which is bing, 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 physical. And down here, I start with these little guys over here, and we end with these little guys over here. It is the exact same picture as the previous one. I'm just realizing that. Good job, Carter. My reactants do not equal my products, so therefore that is chemical. All right, my friends, let's recap this. First things first, chemical changes generally reversible. Generally, but not always, okay? The key thing here is reactants equal the product. That ain't no change, yo. The next thing is chemical changes. They're generally irreversible. My reactants do not equal my products. Hope this helps clear that up. Thanks so much, my friends, and have a sciencey day.